Hi everyone, and welcome back to another AP Calculus video. We're going to continue talking about area under a curve as it relates now to functions, and we're going to look and see if we can find a more precise way to find the area under a curve. Remember, the curve that we're trying to find the area under represents some sort of a rate. It doesn't always have to be a rate, but oftentimes in application problems it's a rate, and when we find the area underneath gives us the amount of change for that scenario. Today we're going to be talking more about functions that don't necessarily have an application associated with them. They're just equations. And so we're going to get really basic and skill-based with finding some of these areas under curves. And we're also going to talk about new mathematical notation to kind of express this idea of getting the area under a curve. But first, let's review a little bit using this cool little Desmos creation. This Desmos creation helps us find this thing called a Riemann sum. And a Riemann sum is basically what we were finding in the first little couple of videos here where we talked about rectangular approximations. The difference is that a Riemann sum isn't necessarily always going to be the same partition width. Sometimes it is, sometimes it isn't. But the idea is we're partitioning our curve into rectangles, and we want to choose the best scenario that gives us the most accurate representation of the area under the curve. So really, you can think of it as a left-handed or a right-handed LRAM, RRAM, MRAM. You can think of it as that and call it that in your head because it's essentially the same concept. So here we have our function. We've graphed it here in blue, and here we've taken our function and we're going to set our boundaries here. Let's set them to -1. We'll go from -1, and then we'll set the end point of our partition here at 2. There we go. So we're going to find the area between -1 and 2. And you'll notice that the area here to the left is red, is represented in red. One of the things we're going to discuss today is this idea that the area above the x-axis is treated as positive area, and the area below the x-axis is treated as negative area. So when we are finding the area under the curve, we kind of think about that negative area as canceling out some of the green area. So you'll notice when we actually see what the sum is, that when we consider negative area kind of cancels away some of the area we're finding. So it's interesting, and we'll discuss that more as we move forward. But if we take a look here at what's happening, we can actually then set and decide where we want our rectangles to have their height. So here it's set for a midpoint, and you can see that our rectangle crosses the curve right at the midpoint of right between the two sides. You can see, and it's set for that midpoint sum. Now, if I make this little thingy go over here to the left, then c equals 0 is a left-handed Riemann sum, or an LRAM approximation. And you can see that the rectangle is drawn, the height being drawn from the left over. And then if I go all the way to the right, where c is 1, you can see that this is an RRAM approximation, and the the height of the rectangle is the right side of the partition. Now, I can also change the number of partitions. And as I do, one of the things I want you to pay attention to are these two values here, I equals, and then this actual area. Today we're going to talk a little bit about this sigma notation, this Riemann sum notation, with this Greek letter E. You should hopefully recognize that as being summation notation. And the idea with Riemann sums is this. Riemann sums say we have a ton of rectangles, and we're going to add up all the rectangles. So when we're adding little partitions, when we're adding thing after thing after thing, sometimes the mathematical notation for that can be more concise is to use this sigma notation. Sigma just means, hey, we're adding a bunch of stuff up. And so f of s sub I times w is simply Riemann's way of saying the height of the rectangle times the base of the rectangle. So you can understand that this sigma notation really just means, hey, we're going to take rectangle 1, find its area, add it to the area of rectangle 2, add it to the area of rectangle 3, and we're going to keep adding them together until we get to the end of our interval. So that's what that sigma under Riemann sums represents. Now, Leibniz, he saw that and he took it to the next level, and he said, I'm not going to use the Greek letter, I'm going to use the Roman letter S. And he created this symbol that we are going to now use moving forward to represent the area under the curve, or the summation of these rectangles. And we'll talk a little bit more about it here in a minute. But this thing that says actual area, and it looks like the letter S, that's called an integral. And it's supposed to look like the letter S because it's the Roman letter S for the word sum. So it's still the same concept of we're taking the height, f of x being the height of the rectangle, times dx, which is the width along the bottom. So that's the change in x, and that's, the Leibniz notation for the change in x. So essentially f of x times dx is just the area of a rectangle. And then S meaning the sum of all the rectangles from A to B. And there's actually a little more to it, and we'll get to it in here in just a few moments. But the idea is that we're taking all these rectangles and adding them all up. And Riemann's is an approximation, whereas Leibniz notation is the actual real deal. So we're going to learn how to find this in the coming days as well. So the actual value of the area under the curve here from -1 to 2 of this function is 0.95644914241. So that's the actual area. Riemann's rectangular approximation is 1.45281254172. So how can we make Riemann's approximation a little better? Well, instead of doing 5 rectangles, I'm going to come up here and I'm going to change it. And look, now we have a bunch more rectangles. And we can see that, look, Riemann's sum is getting closer and closer. And the more rectangles we have, look at all those rectangles. I would never want to do that by hand, ever. Look, it's getting closer to the actual real deal area under the curve. And if I can increase this, up to 100, look how close I get. I'm within, 3/100ths of the actual area. And I can actually get even better approximations by using midpoints. So here's my midpoint approximation. So now I'm using the midpoints of the rectangle instead of the right-hand side. And look, 956, I've gotten myself 4 digits of accuracy. How crazy is that? Using 100 rectangles, midpoints as my heights, I am so much more accurate. What happens when I use the left sum? Well, I go back to being not as accurate. So it's an underestimate here because of the way the shape of the curve with the increasing and the decreasing. But the idea here is that if I increase my rectangles and use the midpoint, really, that's the best way to go, I can get my Riemann rectangle MRAM sum to be really close to the actual area. And this was just kind of a demonstration of what the area under a curve looks like. And so we're going to talk about this integral notation, this S with the A and the B. We're going to talk a little bit about that. We're going to talk about Riemann's notation and how to kind of go back and forth between the two. It's actually pretty easy. But ultimately, we're going to be using Leibniz's S notation. It's called an integral. And it is more elegant, it is more succinct, and it is just the way that we do it here. So we have to learn the language of mathematics. So let's talk a little bit about this. You don't need to copy all of this down by any means, but Riemann and Leibniz found ways to calculate the area under the curve, along with many, many other people. They're just the ones whose names get to be in our books. Riemann sliced the curves into rectangles and added them together. And his way was great, and he wasn't the only one to do this by any means. But you can use different geometric shapes, not just rectangles, varying sides and widths. But Riemann's, generally he used rectangles. And generally he decided the rectangles don't always need to be the same width. And so he said, well, we're going to call this thing the norm is the maximum width that we're going to have in our intervals. Again, you don't need to write this stuff down. But then he said, we're going to divide it up. And the more rectangles we can get, the more accurate and closer we can get to the actual area under the curve. So here's how he wrote this down. He used a limit notation. And he said the limit as the width of the interval. So that's this. So as the width, that's the change in x, right? So in Leibniz notation, this is the dx. So as the width of my rectangles gets closer to 0, so that I just have slivers, I have, instead of a 2-dimensional rectangle, I have a 1-dimensional sliver. As the limit of the rectangle width gets closer to 0, the sum of this would be the height, and this would be the width. Okay? So it goes like this. If this is my curve, and this is my rectangle, okay? He's saying this is f of ci, so that's my height, and then this is my delta x, okay? So that's the idea, and we're taking an infinite number here and adding them together, or, you know, n being a really large number of them and adding them together. So then what Leibniz said is he said, okay, I'm going to do this better, and I'm going to use this other notation. So he got away from sigma and the limit, because not for nothing, but it's kind of gross. And he said, we're going to do this. And he said, we're going to call it the definite integral. And definite means it's defined, it goes from point A to point B, and it represents the area under the curve. So this is Leibniz notation. The integral from A to B of f of x dx. So this is called an integral. The equation that we're integrating is called an integrand. And the process, we're going to refer to it as integration. It is different. You know, integration has multiple definitions in the English language. Here in mathematics, integration refers to the process of finding the area under a curve. So when we consider this function, f of x equals sine of x, we can see that sine of x has both positive and negative values above and below the x-axis. So if I go back up to here to where we looked at it in Desmos, we are both above and below the curve. The green area is considered positive, the red area is considered negative. So when we're finding and evaluating the integral, the idea is that the negative area will cancel out some of the positive area. So when we add them together, your book does a pretty confusing, I think, job of explaining this. But the idea is this is a positive value, this is a negative value. So when we combine them together, we have to add positive numbers with negative numbers, so the negative numbers will cancel some of the value away. So let's talk a little bit about what it would be asking for if we saw this word total area, and we'll come back to this. But total area under the curve refers to basically taking any part of the function that would be under the x-axis. We basically take it and we make it positive. So everything becomes positive. So essentially, we could flip any negative area above the curve, and then it would become positive. And so when we take the absolute value and put absolute value bars around a function and graph it, that's basically what happens. If you had an equation for this graph here with the blue and the yellow, and you put absolute value bars around it, it would look exactly like it does, but that yellow part would literally flip upward, and it would look kind of funky in your graph. So let's talk a little bit about translating between the Riemann notation, in case you see it on your AP exam, and then translating it into integral notation. And then we'll talk a little bit about how to evaluate integrals using area and geometric shapes. In the coming days, we're going to talk about how to evaluate integrals using antiderivatives, and we're going to find a way to evaluate things that don't create nice geometric shapes. We are going to talk about estimating integrals using, you know, LRAM, RRAM, and MRAM, but more often than not, we're going to be using antiderivatives to integrate. But for today, we're going to keep it simple and just get used to this notation. So here's the Riemann sum. If I wanted to write it as what we call a definite integral, here's essentially what we're going to do. This is another way of saying f of x. So here, I'm doing f of some value c, so c sub k. So this is like f of c sub k. So you have to kind of pull from that the original function. So it's essentially, you get rid of the c sub k, and you just write the c sub k as an x. That's literally all you do. So it becomes x squared minus 3x. That's the function. And then it says, okay, we want to evaluate this over a partition from -7 to 5. Well, in my notation, this is the interval. So this is the a and the b. And you'll notice, here's a and here's b. This is where they go in the interval notation. They go right there next to that little integral symbol. So when I write this as an integral, I'm going to start like this, and I'm going to go, this is called my lower limit of integration. So I have a lower limit that goes on the bottom, I have an upper limit that goes on the top. And usually when we talk about the area, we go from left to right, so lower to upper. So bottom is lower, top is upper, usually. And then we put the equation in, so this is f of x, so we say x squared minus 3x, and then we always button it up with a little dx, and I like to wrap up my function with a little set of parentheses, just so I keep it all together. The idea here is that I'm going to take the limits from the partition, and then whatever the equation is, I replace the c's with x's. That's the equation, and boom, I put it in, and that's integral notation. So when you're asked to rewrite a Riemann sum as an integral, this is what you should be doing. Now, let's talk about how to evaluate these integrals. When we evaluate an integral, we're going to remember that really it's just asking for the area under a curve. So for today, we're going to graph these. So step 1, graph. So I'm going to take this line. It's just a line. That's nice. I'm going to graph it. 1, 2, 3, 4. It has a y-intercept of 4. It goes down 2, over 2, down 2, over 2. There we go. And I want to go from 1/2 to 3/2. So 1/2 to 3/2. So I'm going to go ahead and draw those two lines in and shade the area that I want to find. And then I'm going to see which geometric shape it is. So this is the shape of a trapezoid. So the area of a trapezoid is 1/2 the height times b1 plus b2. So now I have to see what my height is. So I'm going to zoom way in here, and we're going to talk a little bit about the shape of this trapezoid, because it's actually lying on its side. It's actually been upended. Whoops. And I seem to have lost my screen. One moment. There we go. So the idea is my trapezoid looks like this. So B1 is actually a y value. So B1, B2, however you want to call them, they're the y values. So the heights, the f of 1/2 is going to be B1. F of 3/2 is my B2. So when I figure this out, I have to realize my y values are B1 and B2. And then this distance here is 1. That's my delta x. Okay, so that is my height of my trapezoid. So my height is 1, B1 and B2, I have to find those. So let's zoom out a little bit so we can find what those are. F of 1/2 equals -2 times 1/2 plus 4. It's going to be -1 plus 4, that's going to be 3. F of 3/2 is -2 times 3/2 plus 4. So that's going to be -3 plus 4, that's going to be 1. So to evaluate this integral, I just need to find the area of the trapezoid. So this integral will evaluate to 1/2. The height is 1, B1 is 3, B2 is 1. So 1/2 times 4, the area is 2. So this integral evaluates to 2. When I'm asking you to evaluate an integral, I'm asking you to find the area under a curve. So let's try another one here. Let's try this integral, and we're going to find the area under this equation from 0 to 3. So it's the same graph, which is nice. 1, 2, 3, 4, 1, 2. But this time, when I go from 0 to 3, I'm going to have some area under the curve. So I'm going to have some positive area up here, but then when I drop down and find the area up to 3, I'm going to have to treat this as a negative area. So this little pink region is going to be negative. So it's like I have two triangles. I'm going to find the area of each triangle, is what it looks like. But then when I combine them, the bottom triangle is going to be a negative number when I add them together. So let's find the area of these triangles. So the green triangle, remember it's 1/2 base times height for a triangle. So the base here is 2, the height is 4. So 1/2, 2 times 4 is 4. So this area is 4, and then the pink area is going to be 1/2. Let's see, the base of the triangle is 1. And then I guess I need to know what this is. I'm going to have to find f of 3. Negative 2 times 3 plus 4 is going to be negative 2. Negative 2. So that means that this side has a length of 2. So the area is 1, but I'm going to treat it as it's negative because it's under the curve. So 4 and negative 1 mean that the total area, I guess not the total area, that's the wrong word, the net area is the appropriate way to describe this. The net area adds together positives and negatives, and when we combine that up, the net area is 4 plus negative 1, or 3. So this integral works out to be 3. That's how we evaluate the integral. We find the area under the curve. Anything that is below the x-axis, we treat it as a negative area, so we can add them together. Now, if the question was asking you to find the total area, then any area would be considered positive. So for the total area, we would say it's 4 plus the absolute value of that area under the curve, or just 4 plus 1, or 5. So total area treats everything as positive. That's how we deal with this. So let's take a look at a couple more integrals here. So when I evaluate this integral, so negative 20, it's a constant. That's kind of weird. Well, remember that when we graph something, y equals negative 20 is just a horizontal line. So from 3 to 7, well, it would be a rectangle. But it's below the x-axis, so it's going to be negative. So one side is 20. This distance from 3 to 7 is 4, right? So 4 times 20 gives me an area of negative 80. So this integral evaluates out to be negative 80. So again, it's just always the area under the curve is negative. Now, when we're integrating a constant, here's a little shortcut, a little notation for this. If you are integrating a constant and it looks like this, so here in the example we just did, c was negative 20, the shortcut would be like you would say c is negative 20, and then b and a were 7 and 3. So we'd say 7 minus 3. So negative 20 times 4 gave me my negative 80. So that would be another little shortcut for when we're integrating a constant. Now, last things last, let's take a look at our calculator, because it's very important to be able to understand how to use a calculator to evaluate an integral. And so I'm going to show you some calculator moves here. Now, let's just make a quick prediction before we pull our calculator out, and I'll show you some buttons and some shortcuts that I know you're going to like. If I want to evaluate this function, here's the graph, by the way. The absolute value of x over x, it's just two horizontal lines that meet at 0, and it's a jump function. So if I go from negative 1 to positive 2, you have a square here, and here we'll go ahead and use our pink and green convention. So you have this negative square here with this green rectangle here. And so what ultimately happens is this pink rectangle and half of the green square cancel each other out. So the area here is just 1. So the net for evaluating this integral, this equals 1. We know for sure 100% it is going to equal 1. So here's how my calculator will help me find this. So here are some great calculator moves that we're going to learn here and use. So in my calculator, oops, oh, it does not want to stay put. Here, we'll put it over here. In my calculator, I'm going to use my Math 9 button. So if I hit my Math key and I go all the way down, we are familiar with Math 8, which is great, but we're going to use Math 9, FNInt, function integration. And here's kind of how it's going to look on a lot of your calculators. When you hit that button, an integral symbol pops up. And so it's pretty easy to see and figure out what am I going to type in. So here's my function. My lower limit is -1. I just type in what I see. Now I know some of you have the older version, and that's okay. I'm going to walk through what that is, so just hang tight for a moment. Now I have the absolute value over x. Here's how I get to my absolute value function. I'm going to hit the math button, and I'm going to scroll over 1 to the number option, and option number 1 is absolute value. So I'm going to hit abs, and for me, I get the absolute value bars. For some of you, you're going to show the word ABS parenthesis. Treat the parentheses like your absolute value bars. Type X in between, and then close your parenthesis if you have that old school operating system. For me and anyone else who has the new one, I'm going to arrow out of the absolute value bars, and I'll type in divided by x. And then I'll type in a dx. Now watch what happens when I hit enter. It takes a little while to calculate the number, but look what it spits out. 1 and then a bunch of garbage. So here's the deal, you guys. We know that the answer should be 1. And if we're going to use Math 9 to evaluate some of these integrals, every now and then we're going to get the answer we should plus a bunch of zeros and then some decimal values. Now, if you get some decimal values other than 0, probably the integral will be, other values. Will be those decimals. But here, anytime we get 1, and we know it should be 1, and then we get a whole bunch of zeros, and then a couple of numbers, chances are pretty good that this is round off error. This is why we round to 4 places. So if we cut this off after 3 places. If we cut this off after 3 zeros, clearly it's 1.0. You see, your calculator uses some methods to evaluate these integrals that cause it to have some round off error. And it's not a high precision method. So it's okay to get this little garbage. We just need to understand and interpret it and know this is why we go to 3 places of accuracy. It's because sometimes our calculator, the methods that it uses to analyze and find these values are sometimes not as precise as we would like them to be. So here's how you use your calculator. Let me talk a little bit about the people who need to use an older calculator. Let me show you how that will look. So for anyone using an older calculator, here's what it's going to look like to evaluate the same exact integral. I'm still going to go math, and I'm going to choose option number 9, that FNINT. And here's what my screen will show. Now the first thing I'm going to do is I'm going to type the equation. So I'm going to type the equation, I'm going to go to math, over to my number option, and I'll hit the absolute value of x, close the parentheses. So again, this is your absolute value bars, divided by x, comma, and then I need to tell it which variable I'm integrating with respect to. So I'm going to say comma x, comma, and then I'm going to give it my limits of integration. -1, comma 2. Close my parentheses. So it's equation, variable, a, b. And when I do that, it gives me what I need to know, and I've got it, and I'm happy, and this is what my calculator screen will need to look like so that I can be successful and get these values. So again, it's equation, comma, variable, comma, a, comma, b. So hopefully this has been helpful for you in getting a foundation on understanding integrals and that whole idea of mathematical notation and the language that tells us to find the area under the curve. So the concept is not new, it's just the language we're going to be using now moving forward are these integrals, and they're not going to go away. So this is going to be the whole rest of Calculus AB is evaluating integrals. So keep with it. You guys, you can do this. It might seem tricky at first, it might seem difficult, but don't worry, a challenge is good for you. You can do this. My experience tells me that you can be successful. So stick with it. You've got this.